We have discussed about heap sort, and we have seen that heap is one kind of data structure which is actually a tree data structure which supports the complete binary tree structure. So first of all, heap is a complete binary tree. Okay, and the next thing is based on the property of the heap, whether it is max heap or mean heap. Based on that, the uh, the values in different nodes will be like this. If it is a max heap, then father value is greater than its left child and also greater than from in right child. If it is a max heap, it means in case of max heap, root is having the maximum element. Similarly, in case of mean heap, father value is less than left child and less than right child. It means the root element is the minimum element. Okay. Now the next thing is, so this is one property, and this is property number two. And there is another important thing, that what is the main application of heap. The main application of heap is, remember this, priority queue. If you remember priority queue, what is the priority queue? In case of priority queue, you can insert elements in any order. Elements can be inserted in any order, but when it will be deleted, it will be based on its priority. It's mean in case of priority queue, along with the data value, there will be some priority value. Along with the data value, there will be some priority value. Okay, and elements can be inserted. Elements will be inserted in normal order, but when we are going to delete the element, we have to delete based on the priority value. So in case of priority queue, if we implement priority queue with the help of a max heap or mean heap, max or mean heap, based on the property of the priority value, sometimes lower priority means higher priority, or sometimes higher priority value means higher priority. So based on that, max or mean heap we can use. Now see what happening in case of max or mean heap. The root element always is the most important element, and we have seen in case of heap sort that we can delete from the root element only. So if I want to delete any particular element from the heap, then first we have to replace the root element by that element. Okay, so first thing is replace the root element with that element, or you can say interchange, one kind of swap operation you have to perform. Then you have to adjust the heap. Then you have to check whether it is satisfying the property of the heap or not. So this is the basic use of heap. So you see, in case of priority queue, if we always able to create a max heap or mean heap, then we can easily delete the maximum priority element. So in case of priority queue, if we this heap, a max or mean heap, is very useful. Okay, so these are the basic properties. Another property, duplicate elements can be present. Duplicate elements can be present because this is not a search tree. Heap is not a search tree. Heap is one kind of data structure mainly for the purpose of this type of things, priority queue. Okay, and we have also seen heap sort, and the time complexity of heap sort is, remember, n log n, because it is a complete binary tree. Complete binary tree having a height always log n. So our heap sort searching time is log n. So if I want to insert n number of elements, so maximum we can move up to log n. Okay, so what is the total time complexity? N into log n. So that is the total thing about heap sort. Now today we will discuss another important data structure, which is also a kind of search tree. So we have also covered one search tree that is called binary search tree, and then we see that binary search tree having some drawbacks. Sometimes the tree can be of maximum tree height can be order of n. So we have moved to AVL tree, okay, which is always try to make the height within log n range. Clear? Now, still this binary search or AVL, see this two type of trees which are search tree, they having maximum, they having maximum children 2. So it means in each level, the number of nodes is 2 to the power I, since it is a binary tree. It means since the number of means in each level maximum number of node is very small, only 2 to the power I, so that's why the chances of height increasing in case of BST and AVL is very high, because we are only considering. Now suppose I have created a node like this of 3 nodes, or say for 7 nodes. This is one tree of 7 nodes. This is a, suppose a binary search tree or some AVL tree, suppose this one. Now I have created another node or another tree like this. So you can easily understand. So this is another tree. This is another tree, but what is the advantage? Again search tree. Again search tree. Search tree means, remember, search tree means father is greater than left subtree values, and less than right subtree values. So this is the normal property of any search tree. Means if you perform in order traversal, of any search tree, you will get ascending order. So this is the property of any search tree. Now see, what is the advantage of this search tree? The advantage of this search tree is height. The height is very small. See, in this particular search tree, the height is level 0, level 1, level 2. So height is 3. Height is here 3, maximum level plus 1. But in this case, this is level 0, this is level 1. So height is only 2. So height is decreased. How we can decrease the height? By increasing number of children in each level. In binary tree, it is 2 to the power I. If we somehow create a ternary tree, then it will be 3 to the power I. If we create a quaternary tree, then it becomes 4 to the power I. So it means with the increase of number of children in a level, we can easily reduce the height. Height reduce means I am just decreasing the time complexity. I am decreasing the time complexity. In this BST or AVL, the time complexity is order of log n base 2. In this type of heat tree, the time complexity becomes log n base 3, or based on the maximum number of children. So automatically the value will be decreased, height will be decreased. So this will create a another level of search tree, which is called M-way search tree. Okay, multi-way. M-way means multi-way search tree. And remember here, M is what? M is the order of the tree. Order of the tree. What is the order? What is order of a tree? The maximum number of children in a node is defined the order of the tree. Okay, and remember, in case of M-way search tree, the order of the tree is always greater than 2. It means number of children is always greater than 2. So based on this M, if it is having 3 children, it will be called 3-way tree. Okay, if it has 4 children, it will be called 4-way tree. So this 3 or 4 is actually representing the order M. Okay, now see, when we increase the number of children in each level, automatically the height will be decreased, our searching time will be decreased. So this is the main goal of multi-way search tree. There is one kind of multi-way search tree which is called balanced multi-way or M-way search tree, or sometimes this is also called very popular name, which is B tree. Remember, B tree is not a binary tree. B tree is not a binary tree. B stands for balanced, and B tree is always having order greater than 2. It is never binary tree. It is balanced multi-way search tree. What is the meaning of balanced? Balanced mean here balance means all the leaf nodes are at same level. This is the actual definition of balanced. Now see, in case of AVL tree, there is a chance that your tree is like this. It means all the leaves, this is one leaf node, this is another leaf node. All the leaf nodes are not in same level. It means if I want to search this particular element, suppose the elements are like this, this is 10, this is 5, this is say 15, this is say 11. Okay, now suppose I am searching 5, then how many comparison I have to perform? First I will compare with the root element. Since my element 5 is smaller than root element, so I will move into this position. So how many searching I have to perform? I have to perform 2 searching. Now what is the height of this particular node? The height of this particular node is 2. See, this is level 0, this is level 1. So maximum level plus 1. So height of the, so we are actually searching up to height. Now if I search 11, then first I have to compare with this. Then 11 is greater than this, so I will move into this side. Again 11 is smaller than this, so I will move into this side. So I have to compare 3 times. And what is the height of this particular node? The height of this particular node is, this is height level 0, level 1, level 2, so height is 3. See, when I am searching any particular element, what actually I am doing? My search time is always equal to height of that node. Now what is the maximum time complexity or worst case time complexity? Obviously the maximum time complexity or worst case time complexity, you can say it is of order of log n, but if you see properly, that it will not give you the exact value. It will not give you the exactly a log n value, because this is not all the leaf nodes are not at the same level. If your tree is like this, then you can say my search is order of log n. If your tree is like this, then you can say that all the leaves are at same level, so my maximum search time is same. See here, one leaf is in this level, another leaf is in this level, so your search time is varying based on the leaf node. But in this particular structure, all the leaf nodes are at same level, so you can say in this type of picture that my searching time complexity is exactly this. But this type of picture, your searching time complexity is not exactly like this. So it has been calculated and seen that the worst case time complexity for AVL tree, worst case time complexity for AVL tree is order of 1.44 log n. Okay, it has been calculated some using some formula that this 1.44, if we multiply the order of n with this 1.44, it will go as much close as its actual height. It will go as much close as to its height. So remember this, that the worst case height, or you can say time complexity of any AVL tree is actually 1.44 log 2n. So since it is 1.44, if you remove the decimal values, it will still give you 1. That's why we use log n. But if you calculate it properly, it will give you this. But if your tree is like this, then it will always give you exactly log n value. Okay, why we are getting in this type of structure exactly log n value? Because here all the leaves are at same level. So based on this property, this balanced multi-way search tree is developed. So in case of balanced multi-way search tree, all the leaf nodes are at same level. So for all the leaf nodes, you will get exactly the same. Means for all leaf nodes, the time complexity, searching time complexity is almost same. Okay, so that's why this balanced multi-way search tree or B tree creation is little bit different from the AVL tree or binary search tree. In case of binary search tree, we generally create the tree. First we create the root, then we go for left child or right child. So it is always top to down. We create the tree top down format. But we will see in case of B tree, the creation will be in reverse order. It means from leaf node, we will try to generate the root node. From leaf node, we will try to generate the leaf node. Okay, so this is the difference in balanced multi-way search tree and B tree. Obviously, the number of children is one difference between these two. Okay, so now let's move to how to create a B tree, or first what are the different properties of a B tree. The property number one for a B tree, remember, now I forget to ask you one question. Can you tell me why we draw the tree always root in upside and then the branches in downward format? But normally our tree in normal life, we have a tree like where root is in this position and then the branches like this. Okay, but when we draw a tree in our AVL tree or this type of thing, we draw first root, then we go downward for the branches. Why? Just think about this and then tell me. Now we are moving to this B tree properties. So the property number one is in case of any multi-way balanced multi-way search tree, the root node having root node has at least at least one key value, at least one key value, and at most m minus 1 key values. Now what is the meaning of this key values? Let us try to understand. See, when we are discussing the AVL tree or binary search tree, AVL tree or binary search tree, this node having some values, na? And I told you that this value is called the key value. So suppose this is having 10, this is having say 5, this is having 7, this is having 15. So these are nothing but key value. That's why we also told, we also say that in case of BST or AVL tree, there will be no duplicate elements. Okay, because they are key values or unique values. So now see, if we increase, so if there is only one key value, if there is only one key value, then based on that key value, what we can decide if any key value is less than this or greater than this. Clear? Now in multi-way search tree, what we are drawing, we are having more than two children. Okay, now if there is only one key value, say k, then based on that value, I cannot generate three different solutions or three different conditions. For a single key value, we can only have either having some value less than that key value or greater than that key value. These are the two only possible solutions. But if there is three children, then obviously it should have more than one key value. Okay, so the logic is like this: if there is only one key value, say k1, then we can only generate two different children maximum, because based on this key value, one should have less than and another should have greater than. Now if I add another key value here, now see what we can do. From this particular value, this particular children is less than k1. This particular children, this one is in between k1 and k2, and this particular children is greater than k2. So based on that, we can say we have three children. So it means if there are m number of children, m is the order, m number of children, m is the order, then how many key values there will be? There will be m minus 1 key values in a node, key values in a node. So I hope it is clear. So let us take some example. So for simple example, suppose there is a key value 5, there is a key value 10. Any value less than 5 will come into this position, suppose 4. Any value greater than 10 will come into this position, say 15. Any value in between these two will come into this position, suppose 7. So this is the logic of more than having more than two children. If there is more than two children, then obviously the number of key values will be increased. We have to increase because there is only two possible cases for one key value. So that's why we have to create more than one key value in a multi-way search tree. Okay, so that's why we are writing root node has at least minimum how many key values? 1. It means root can have minimum two children. Minimum. See, because minimum one key means minimum two children, and maximum how many children? Maximum is this amount of children, then there will be k minus 1 key value. So that's why m minus 1 key values. Okay, for root. Now the property number 2. So this is for root node. Now if it is not root node, so for other nodes, the other nodes except the root node, for root node we have already told that minimum one key and maximum m minus 1 key. The other nodes except the root has contain how many values? Contain at least, so this is very important, this particular value, at least ceiling m by 2, sorry, m by 2 minus 1. Okay, this is very important. Ceiling m minus m by 2 minus 1 key values. Okay, and there is a minimum as well as maximum. At most same m minus 1 key values. So this value is very important. Remember this, because when we delete some node from a B tree, we have to maintain this property. This is very important. So if the order of the tree is say 3, then what is the minimum number of key values that a node contain? For if it is not a root node, then it is 3 by 2. It means it will give you 1 point something. It means we are taking the ceiling value, so it is 2 minus 1. So this is the minimum value. Okay, and maximum. Now see, for 3 it is not that much important, but for 5, see, for 5 it becomes 5 by 2. If order is 5, 5 by 2 mean it will give you 3 minus 1, it is 2. So minimum 2 number of key values is must for a node except root node. Okay, so now this too is very important property, and one property I have already told, that all the leaf nodes are at same level. This is very important. All the leaf nodes are at same level. I've already discussed why we require all the leaf nodes are at same level: to maintain a fixed time complexity. To maintain a fixed time complexity for each and every node, we have to maintain this property that all the leaf nodes are at same level. And you will see when I will create the B tree, you will see why all the leaf nodes are at same level. Okay, now property number 4, this is again important, that key values are arranged key values are arranged in a uh, defined order, in a defined order within the node. Normally the key values are arranged like this: k1 is less than k2 is less than dot dot dot, like this. So this is the uh, normal property of key values, that key values are in ascending order. Okay, so these are the 4 properties that we have to maintain when we will go to create any B tree. Okay, now let us start to create a B tree of some values, so, and with specific order. Now suppose we have some values like this. We have say 5 to 10. Let us let us take some uh, let us take some alphabetic order. A, sorry, just like AVL tree: A X B Y C Z D W E V. Okay. And we have to create a tree of order say 3. Okay, so order 3 means maximum how many children it can accommodate: maximum 3 children. Okay, so what is the maximum number of key values that we allowed? We allowed maximum key value is m minus 1, that is 3 minus 1, that is 2. So this is the maximum key value in a node. Okay, see how we will create this. So a, so this is the only, this becomes the root. Then we add x, x is greater than a, so it will be added next to a. So these are the key values. So this is key value 1, This is key value 2. They are in order like this, k1 greater than k2 like this. Okay, now we will add b. Okay, now if we put b and b is one key value, then it will look like this, abx. So this is k1, this is k2, this is k3. They are in ascending order. Now see, if I draw a tree like this, then it will not satisfy this one, because maximum key value that is allowed in a particular node is 2, because order is 3. So what we have to do, so there comes, this is called overflow. This is called overflow for a particular node. Now what we have to do, how we can solve this, we have to split. So there comes one algorithm, you have to split the node. How we will split? We will split the node based on the median value. Based on the median value. Okay, now see, this median value calculation is very simple. If there is odd number of elements, if there is odd number of elements, then median calculation is very simple. What is the value of median? If there is odd number of, say, x number of elements, then the median becomes x plus 1 divided by 2. That will give you the position. So there is this is 1 2 3 elements, x is 3, so 3 plus 1 divided by 2, that will give you 2. So this becomes the median element. 2 is the median element. But if there is even number of elements, then it becomes a little bit difficult, but we will follow the same formula for this. So, and we will take the ceiling value for this. So it becomes like this. So take the ceiling value, so it becomes 3 plus sorry, so if so suppose in this case the order is, say, m is, say, 4, not 3. 3 is the order. So now suppose the order is 4. So when we will split when number of key value is 4. So number of key values when become even. So 4 plus 1 divided by 2, take the ceiling value. So it will give you 5 by 2, it means it will give you 3. So if there are 4 elements, then you have to consider the third one as the median. I hope it is clear. If your order is even order, if your tree is even order, then it becomes little bit difficult to choose the median value. If it is odd order tree, then it is very easy to understand which one is median. Now what you have to select from this? So when there is overflow, you have to choose the median value. And what is happening after choosing the median value? See, your picture will be like this. Median becomes the root, and the left child or left hand key value becomes the left child, right hand key value becomes the right child. So that's why I'm telling you that the B tree is generated from bottom to down to top, or bottom to top order. Here from this leaf node we are generating the root element. Now see, leaf nodes are at same level. Okay, so this is the concept of splitting of a particular node in a B tree. So based on the median value, what you have to do, median value becomes the father. That's all. Median value becomes the parent or father. That's the logic. Okay, now after this, what we have to do after adding? So I have already completed a, x, b. Now the next thing that is coming is y. So again I have to follow the same thing like binary search tree. First I will compare with b. Y is greater than b, so it will come into this position and it will be inserted into this. So b, this side a, this side x, then y. This is key value 1, key value 2. They are in ascending order. So ax, by, c. Now the next thing that is coming is c. So again I will compare with b greater than b. I will come into this and it is less than x, so it will come before c. So your picture will be like this: b, a in this side, c, x, y. Again, this node is overflow. Okay, so what is the logic? If there is overflow, we have to choose the median. Here, which one is the median? X is the median. You can write it. X is the median. Okay, then what you have to do? This X becomes the parent or father of this C and Y. So you can think about same like our AVL tree, that I am only considering this one. I am only considering this one. Then what will be the picture? The picture will be like this: X, this side C, this side Y, and then this is added to B and this is added to A. Now see, I can draw a picture like this, but this is not satisfying the property of B tree. Why? Because in B tree, all the leaves are at same level. So what we have to do? This X will be included into this node. So your next picture will be like this: B, then X. The left of B is as usual, and the middle, see, C is in between X and B. So C will come into this position, and Y is greater than X, so Y will come into this position. So all the leaf nodes again are in same level. Okay. So next, after adding C, what is the next? It is Z. So if I add Z here, so first I will compare Z with this root node. Z is greater than B. Okay, now remember this thing, always see here Z is greater than X. It does not mean that you will add Z into this position. Remember, you have to add the new node will be added, remember this will be added at leaf node. Remember this, always you have to add the new node at the leaf node. Okay, so Z is greater than B, greater than X, so it will come into this particular node. So your picture becomes like this: BX, this side A, C, and this side Y and Z. Okay, after adding Z, so AX, BY, CZ, DW. So D, next is D. So see, D is greater than B but less than X. So it will come in between. So it will come into this particular node. So D will be added into this node. So picture is BX, this side A, in this C, then D,